Hello everyone, this video is going to be on properties of exponents. So we're going to look at how exponents originate, where they come from, why they're used, and then the rules that we most commonly use them for. So to begin, what does 7 to the 4th mean? 7 to the 4th means 7 times 7 times 7 times 7. We're not looking for the answer, we just want to make sure we know what this notation means. Instead of writing all these 7's out, we can just say 7 to the 4th power. It makes it easier for us to write when doing mathematics. For that reason, x to the 5th is actually x times x times x times x 5 times. Moving on down here, if we have 7 squared times 7 cubed, that's like saying 7 times 7 for the first part, the 7 squared, times 7 cubed, which is 7 times 7 times 7. So in the end, this is really 7 to the 5th power. 1, 2, 3, 4, 5, 7. 7 to the 5th. We can do the same thing with x's. Here we have x to the 4th, which is saying x times itself 4 times. Here we have x to the 3rd, which is saying x times itself 3 times. Together we have a total of 7 x's being multiplied together, so we have x to the 7th. If we look at what was happening, we see that we had 7 to the 2nd and 7 to the 3rd, which resulted in 7 to the 5th. If we add 2 and 3 together, we get 5. In this example, x to the 4th times x to the 3rd, add 4, add 3 together, you get the 7 power, which is our result. So the general rule is if you have the same bases, you add the powers together when you multiply them. So a is to the m plus n power. Okay? Let's keep on investigating that rule a little bit more. Say we have some blob, 5 to the 4th, and then that quantity is squared. Well, that's like saying that blob twice, and that blob is 5 to the 4th. Well, 5 to the 4th is really 5 times 5 times 5 times 5, and then there's another 5 times 5 times 5 times 5 being multiplied together. So how many 5's do we have multiplied together? We have a total of 8. So it's 5 to the 8th. Okay, let's do the same thing with x's. We have this blob, and that blob is being multiplied by itself 4 times. So our blobs, I should draw my blobs first. We have blob times blob times blob times blob. 4 blobs being multiplied together, and the blobs themselves are x to the 3rds. And x to the 3rd can actually be broken down into x times x times x, x times x times x. Yeah, I said that right. So how many x's do we have being multiplied together in total? Well, we have 3, 6, 9, 12. So this is actually equal to x to the 12th. Okay? Same thing can be done if we don't have the same thing inside the parentheses. This is just like saying x times y times x times y times x times y. Doesn't matter that the x's aren't right next to each other, they're still being multiplied. So we have 3 x's being multiplied together, 3 y's being multiplied together, so it's x to the 3rd, y to the 3rd. Okay? We're going to leave this example for you to do, but the answer is a to the 4th times b to the 6th. Alright, see if you can use those rules to get that answer. But the general rule is this. A to the m, that quantity to the n power, you multiply the exponents. So here we have 5 to the 4th squared. So 4 times 2 is 8. 5 to the 8th. 5 to the 8th. 3 times 4 is 12. Our answer was x to the 12th. And here, the 3 was distributed down, so we have x to the 3rd, y to the 3rd. Here we have a squared times 2, a to the 4th, b cubed times 2, b to the 6th. Okay? Let's use that same rule, but now with fractions. Everybody loves fractions. So here we have some blob to the 3rd, so blob 3 times, so that blob is 2 to the 5th, 2 to the 5th, 2 to the 5th. Multiplying fractions, we multiply the numerator, so we have 3 2's and we have 3 5's. Notice that the exponent was distributed to both of those, the 2 and the 5. Same thing can be done with variables. We have something to the 4th power, so it's something times itself 4 times. That something is x over y. We have x times itself 4 times, and y times itself, that's a y right there, 4 times as well. That 4 was distributed to each. Okay? And again, I'm going to let you try this hard example on your own. But the answer is 6 squared times z squared for 4 squared times b to the 4th. Okay? And here's the rule. The rule is if you have a over b, that quantity to the m power, you distribute that m to each part of the fraction, to the numerator and also to the denominator. Okay? Continuing with fractions, let's say we have the same base, 2 and 2, but they're to a different power. Well, let's go back to our original rule. What do exponents mean? Well, 2 to the 8th means 2 times itself 8 times. So 2 times 2 times 2 times 2 times 2 times 2. Over 2 times itself 5 times. Well, in the numerator we see these are all being multiplied together. And when you multiply, you can take out common factors. Well, there's a common factor of 2 in the numerator and 2 in the denominator. So they can reduce to 1. Oh look, there's still some more common factors of 2 between the numerators and denominators. We can cross all those out, so we're just left with 2 times 2 times 2. And there's actually a 1 in the denominator. So this is really just 2 to the 3rd over 1 if you want to think about it like that. So those factors of 2 in the numerator reduce with the factors of 2 in the denominator to just leave 2 to the 3rd power. If we have a to the 6th over a to the 2nd, it's like a times itself 6 times over a times itself twice. We see factors of a in the numerator and denominator. Numerator and denominator, those go away. So we're left with 1, 2, 3, 4. So it's a to the 4th. Okay? So how are we getting this? We see 2 to the 3rd here. What's the relationship between the exponents? The relationship is subtraction. So 8 minus 5 is 3. 6 minus 2 is 4. So if you have the same bases, you can subtract their exponents when you're dividing to get the result. So a to the m minus n is the rule when you're dividing with the same base with exponents. Okay. Let's keep on that line, but let's say we have a fraction that has a smaller exponent at the top than in the denominator. So this means 2 times 2 times 2 over 2 times 2 times 2 times 2 times 2. So again, let's eliminate our factors of 2 from the numerator and denominator, and we're left with 1 on the top because 1 is always being multiplied. And then you have 2 to the power of 2 on the top. Okay? So that's our result when we do it from our basic logic. Now, how was this, how is our rule executed here? So our rule says take the power of the numerator minus the power of the denominator and you get your result. So if we take 3 minus 5, that's negative 2. But we also know that this is equal to 1 over 2 squared. So these two things are equal. One by our logic of the rule and one by our logic of exponents. Let's continue on with this with variables. So we have x times itself 5 times over x times itself 8 times. 1, 2, 3, 4, 5, 6, 7, 8. If we reduce with our factors on top, with our factors on bottom, we're left with 1 over x to the 1, 2, 3x's third power. Again, let's apply our rule from the previous page. Numerator minus denominator exponents, we have x to the negative third. So we're seeing this relationship. Here we have x to the third in the denominator, and here we have x to the negative third. 2 to the second in the denominator, 2 to the negative 2. So this pattern is coming about some relationship between the negative and a fraction. Okay? Let's look at, say they have the same exponent. So we have 3 times 3 times 3 times 3, 3 times 3 times 3 times 3 times 3. If we reduce all of these, we're not left with 0. Remember, there's actually 1's being multiplied here, so we're left with just a plain old 1. If we use our rule, we see that we have 3 to the 5 minus 5 power, which is 3 to the 0. So 1 is the same thing as 3 to the 0. Let's do it again with variables. X times x times x. These reduce, multiplied by 1 on top and bottom still. So we're still left with an answer of 1, and x to the 3 minus 3 power is still x to the 0. So we see that 3 to the 0 power is 1 and x to the 0 power is 1. Well, what is that all about? Well, the rule is actually a to the 0 power is 1. Anything to the 0 power is 1. 176 to the 0 power is 1. If it's to the 0 power, it's 1 because all these factors cancel with each other and you're left with 1. That's the reasoning behind it. And the other rule we were discovering up here is if you use that subtraction rule, you're going to see that if you have something to a negative power, it's the same thing as writing it 1 over that to the positive power. So we have x to the negative third, same thing as 1 over x to the third. 2 to the negative 2, same thing as 1 over 2 to the 2. Okay? So that's our rule. Now let's investigate this just really quickly with a table. It's given that 3 to the fourth is 81, 3 to the third is 27, 3 to the second is 9, 3 to the first is 3. So we're seeing the powers are reducing by 1. So the next power would be 3 to the 0. And we know from our rule that 3 to the 0, anything to the 0, is 1. Alright, let's reduce our power again. 3 to the negative 1. Something to the negative power is 1 over that something to its positive of that power. So 1 over 3 to the first. Next, 3 to the negative 2. That is the same thing as 1 over 3 to the second power, but we know what that is. That's 1 over 9. We can do that again. 3 to the negative third power. That's 1 over 3 to the third, which is the same thing as 1 over 27. Now let's look at these denominators. Here we have 3 to the negative 1, and that's 1 over 3. Notice 3 to the 1 was 3. 3 to the negative 2 was 1 over 9. 3 to the 2 was 9. 3 to the negative 3 was 1 over 27. 3 to the 3 was 27. The pattern you should be noticing is that when we take a negative power, a base to a negative power, it's 1 over whatever it is to the positive power. So we're seeing 3 to the third is 27, so 3 to the negative third is going to be 1 over 27. If we look at 3 to the negative fourth, that's going to equal 1 over whatever 3 to the fourth is, which is 81. So that pattern continues with anything that you have. Okay? And we're going to skip down to one last rule over here. And that is, let's cover it up a little bit. We're going to look right here. 4 over 5 to the negative 2 power. Okay? So if we were to use our rules that we already know, we know that if we have some exponent to this whole quantity of fraction, we're distributing this exponent to each part of the fraction. So this is really 4 to the negative 2 over 5 to the negative 2. This can be written as 4 over negative 2 over 1, because when you multiply fractions, you're multiplying numerator and denominator, so 4 to the negative 2 times 1 and 1 times 5 to the negative 2 is equivalent to this fraction. And we know from negative exponents, we flip them into the opposite location. So 4 to the negative 2 is really 1 over 4 to the 2, and 1 over 5 to the negative 2 is actually 5 to the 2 over 1. So this rule over here, where you have something to the negative n power, that's actually just flipping whatever location it's in. So if it's in the numerator, it's going to flip to the denominator. If it's in the denominator, it's going to flip to the numerator. If you don't see a numerator and denominator, it's always in the numerator. Okay? So this new fraction, if we combine it, we have 5 squared over 4 squared. Okay, this was our answer. How did it compare to the original? Well, it looks like the fraction flips, so 5's on top now, and we have each to the positive 2 power rather than the negative 2. Another quick example, we have x over y to the negative third. Well, that simply means x to the negative third, y to the negative third, which is the same thing as x to the negative third over 1 times 1 over y to the negative third. That negative 3 means flip and keep it to the positive power. And when we bring that back together, we have y to the third over x to the third. So the rule is this. If we have some a over b to the quantity, that whole quantity to the power of negative n, we're going to flip so that the b, what was in the denominator, is now in the numerator. What was in the numerator is now in the denominator, and we take it to the positive power. So it was to a negative m, now it's to, each is to a positive m. So it's that flipping of it. And here's a little something for you to try as well. Some examples for you to practice. So make sure that you can get these right. A to the negative 2 is 1 over a squared. 1 over b to the negative 2 is actually just b squared. 3 to the 4th times c to the negative 5th is 3 to the 4th over c to the 5th. And m to the 3rd over m to the negative 2 is actually m to the 5th. You should try this last one with the division rule that we used on the front page, and also the a to the negative n rule. Okay, try it with both and see if you get the answer. Alright, so this has been a brief overview of the properties of exponents.